On behalf of CSAFE, I want to welcome you to the Spring 2021 webinar series, sponsored by NIST. My name is Anthony Greider. I'm the Learning and Development Specialist here at CSAFE, the Center for Statistics and Applications in Forensic Evidence. This presentation is assessing footwear examiner performance. Our speaker today is Corey Katz. Corey comes to us from the University of California, Irvine. He has been working with CSAFE during his time as a graduate researcher at UCI, and he's been working through the Department of Statistics. So Corey, welcome. Thank you for being here, and I'm going to let you take over.
Thank you. All right, so today I'm going to talk about how to evaluate the reliability of randomly acquired characteristic identification in footwear impression evidence. This is joint work with Naomi Kaplan Damari and Al Stern at the University of California, Irvine. And here's my email address in case you have questions after the presentation. So the objective of this presentation is to introduce you to the statistical framework that we've been working on that will help us measure the variability in RAC identification. So randomly acquired characteristics are, I'll be using the term RAC throughout the presentation. So just an outline of this presentation, I'm going to start by discussing shoe print examination process. Then I'll discuss the data we have. I'll discuss the first attempt at measuring this variability through matching. Then I will dig deeper into something called the staple algorithm, which is used to estimate examiner characteristics. I will then introduce the new model that we've been working on, which is a hierarchical model for also estimating the examiner characteristics. And then I'll close with some ongoing work and future work that we plan on doing. So to start with shoe print examinations. So the idea of shoe print evidence is that a shoe print is found at a crime scene, and examiners would like to find the matching shoe that left that shoe print. People are generally interested, whether it be in court or criminal investigations, in finding the source of the shoe print. But in many cases, it's very difficult to do this. As you can see on the right, we have a picture, there's a partial print, and then we have two shoes that have the same tread pattern, but we don't know necessarily which one of these two shoes left the shoe print because they have very similar treads. So a general shoe print examination process, this is not true in every case, but generally the first step is to rule out any shoe that doesn't match basic characteristics. So as you can see in the image, the shoe print has a very specific tread pattern, while the shoe that they found has a very different tread pattern. So by doing that, we could eliminate a certain portion of the population of shoes. So the next step, if there are multiple shoes that match on these types of characteristics, in many cases, people start to examine randomly acquired characteristics. And I'll talk a little bit, the main point of this webinar is to discuss this aspect. So I'll discuss what randomly acquired characteristics are in the next slide. And then finally, putting all this evidence together, a decision is made based on the strength of evidence, whether or not the suspect's shoe left the print at the crime scene. And again, this is not necessarily everyone's path of a shoe print examination. In the particular data that I'll be using, this is how it is done. And again, I'll be focusing on randomly acquired characteristics. So first, what is a RAC? So a RAC is marking on a shoe. Generally, the most common types are scratches and holes that form on the sole of a shoe as you wear them. So basically, you step on a rock, you could create a scratch or a hole in your shoe, and that would be a RAC. And in most cases, they are considered unique because generally people don't have the same markings on their shoe soles as other people. Just common things that are not considered RACs are like manufacturer defects, pattern, like the overall general pattern of the shoe is also not considered a RAC. So you have to kind of differentiate between what was created randomly and what was supposed to be there. And the point of RACs in shoe print examination is to better assess your evidence. So if a RAC appears on a crime scene print and it doesn't appear on your suspect's shoe, that's evidence that that might not be the shoe that left the print. If there's a huge RAC on a shoe and the crime scene print, then that's more evidence that that is the shoe that left the print. So that's why RACs become such an important part of the shoe print examination process. But there are challenges with RAC identification. So these are just a few that are kind of the main focus of pretty much the motivation of what the research that I'm doing is trying to hit. So the first one is that you need the physical shoe to find RACs. So as I mentioned, manufacturer defects, tread pattern, there could be little inconsistencies, and those are not necessarily considered RACs. So if you just create a shoe impression, you might see these things as RACs, but you actually need the physical shoe to be able to differentiate between. Another big one is that RACs are not always identified by every examiner. So if multiple examiners examine the same shoe, a RAC might not be found by one or the other based on size. Also, definition of RACs kind of are varied across shoe print examiners. And also a key point here is that examiner's ability might make it more difficult to find RACs or not, which is a focus of this webinar. RACs could also change over time, so they could get worse. If you have a hole, it could continue to spread. But if it's a small RAC wearing the shoe, the tread usually like disappear. It wears down, so it could make RACs disappear. That becomes a problem if a suspect shoe is found weeks after the shoe print was found. If they continue to wear the shoe, that could become an issue. And then presence of RACs might not always be consistent between lab prints and crime scene prints. So if the crime scene print is a partial print, or if it's not as deep of an impression, it might not have picked up small RACs. But when you make a crime scene print, when you make a lab print out of the suspect shoe, more markings could appear and vice versa. So just more motivation of why we care about understanding this variability in RAC identification. So the first is that we need a strong scientific foundation to trust our evidence. So we have to understand that there could be differences or not in RAC identification. The next big key here is that research is generally done on the final decision. So whether or not the suspect shoe matches the crime scene print. So there's been a lot of research on whether or not examiners could reliably determine that, but not much has been done on the RAC identification itself. And because it's such an important part of in many cases of the process, understanding the differences that could occur in that step is very important. So now I'm going to go into the data. So now that I've kind of laid out why we want to do this research, I'm going to go into how we're doing this research. So our data is consistent of real shoe images and lab prints. We do not, right now, we don't have crime scene prints involved in our research. So as you can see on the left, we have a picture of the real shoe and then the lab print associated with that shoe. And then just to give you an example of some of the RACs that might appear in our specific data set, this area on the right is very prone to RACs, as we see. So you can see some of these triangles that appear in the physical shoe picture, they don't necessarily show up that much. And again, it's difficult because this could just be wear, but it could also be considered a RAC. So just a little more specific on the data. So this data is from a pilot study conducted by CSAFE and the Israeli National Police Division. of identification forensic science. We have 20 total shoes, so 10 pairs of shoes. They're all the same New Balance brand, and they are all worn by police officers. So that should simplify our analysis quite a bit, because now we should have similar wear patterns because they're all worn by similar people. Obviously, there's variation there. And also, we have the same brand, so the materials should all be the same. So if there's an area prone to RACs, that should be consistent across the shoes. And then we have 4 different examiners examining the shoes, but note that they are student examiners that receive some training. So this is really important data, because when we try to measure the variability of RAC identification, we need data where multiple people examine the exact same lab print. So this data has repeated examinations. So we actually have where the same examiner examined the impression twice. We also have different examiners examining the same impression. Some of the shoes we have all 4 examiners examining. And then, although we're not going to touch upon it today, we also have examinations over time. So as the shoe was worn, it was examined at different time points. Again, this data is very limited because within each of these 3 groups above, there's only a few examinations of these types. And I'll get into that a little bit more in the next few slides. And then again, the examinations are not performed by professionals, so that also limits our data quite a bit. The variables collected on these RACs, this is just for this data set, so this could vary quite a bit depending on the examiner, what certain groups choose to collect. In this data set, we have a location of the RAC, and this is defined as the X and Y coordinate of the center of gravity of the RAC in 2-dimensional space. Then we have the estimated area of the RAC. So in this particular data set, a computer-aided software was used, so we're able to estimate the area. We also have the type of RAC. Again, like I had mentioned before, scratches and holes are generally the most common, but we also have a few other types. Again, this is not necessarily the same across every examiner. And then we also have orientation angle, which is the angle of the RAC with respect to the origin or a standard grid. So now that I've discussed kind of the data we have, our first kind of attempt at understanding the variability was to look into kind of matching the RACs across different pairings of shoes. So basically, to understand if RACs were found multiple times by the same examiner and so on. So basically, like I was saying, we have different pairings of shoe impressions. So a pairing in this case is any 2 impressions. So impression A done by some examiner and impression B examined by another examiner or the same examiner. So we kind of broke this down into 4 groups, and these groups are going to be used to understand how the variability is different among different types of examinations. So in our data set, we have 9 shoe impressions that were marked twice by the same examiner. So an examiner examined 1 shoe and then they examined it again. So that would be, so that group is considered a pairing in our case. Then we have a reproduced pairing. So this is when anytime a impression was marked by multiple examiners. So there were a few times where they were actually marked by multiple examiners. So we have a total of like 47 pairings. We also have these over time. So if shoe A was marked at time 45 days, and then it was marked again at 90 days, we could look at the, we're gonna look at whether or not the RACs match across those 2 different examinations. So this is kind of considered like an examination pairing. So each time a shoe is examined, it could be grouped in one of these. So just again, to kind of push across this point of pairings, shoe impressions in this data set are kind of defined by three attributes. We have the physical shoe, so say shoe A from this person, left or right, so we have both. Then we have wear time, so was it worn at 45 days, 90 days, I'm sorry, was it examined at 45 days, 90 days? And then we also have the examiner, so we have 4 examiners in our case. So again, this is just to reiterate what the previous slide had. For example, repeated pairings are the same shoe, same wear time, same marker or exam, and then so on. So the way we match racks is that for each pairing, so say we take 2 of the examinations, we define a similarity measure between 2 racks, one from the first examination and one from the second examination. And then we basically create a similarity matrix across all pairings. So all racks in examination 1 are their similarity to all racks in examination 2. And then using this similarity matrix, we perform maximum weighted bipartite graph matching, which I will talk more about. So again, the idea here is to, we have 2 sets of data points, basically the 2 examinations. So this corresponds to a bipartite graph matching problem. And the idea of the algorithm is to find the best match possible. Now, a lot of the time, these are perfect matching. So every rack would be matched in the entire set. So to avoid this, we do a little bit of pre-processing to kind of cut off our similarity. So I didn't mention it, but we do use 2 different similarity matrices. They are built using all 4 of the variables that I discussed before. So all variables are considered here. And then the picture on the right is basically just a graphical representation of the matching. So we have impression 1, it has all the racks in it. So just for simplicity, we have 3 racks. And then we have 4 racks that were found in impression 2. Again, these could be the same impression or different impressions based on whatever grouping we're in. And then in between, we have the distance or the similarity between the racks. So you could see that rack 1 was similar to rack 1 in impression 1 was similar to rack 1 and rack 3, but not similar to rack 2 and rack 4, and so on. And then the blue lines indicate our matching. We actually restricted further to the 1-to-1 matching. This picture shows like rack 3 is matched to 2 different racks. But there could be unmatched racks. And again, the size of the number of impressions could also be different across, depending on how many the examiner found. So here's an example from our data set. Basically, we calculate the distance between the racks. So if you notice, there's 2 different shapes in the plot. The circles are from the first examination. This is a repeated example. And then the triangles are from the second examination. And blue indicates which ones were matched, and pink indicates which ones were not matched. So now some results we get from the repeated results, like I mentioned, there are 9 pairings. So for pairing 1, for example, 59 racks matched, and then there are a total of 88 possible matches, and that's determined by the minimum of the 2 different numbers of racks. So 88 racks were found on examination 1, but then 93 were found on the second examination. So the total number of possible matches is 88 because we do 1-to-1 matching. And that gives us a proportion of matching of about 67%. And then this is done for every single pairing, which brings us to this table, which is aggregated results. So for the repeated, we see that there are 9 pairings, and we had a mean proportion of matching of about 62%. Again, that mean is the mean of the 9 from this slide. So these 9 values average. And then we do that for the 47 reproduced, the 94 over time, and then the 3017 random. And again, random matching is just everything else that doesn't fit into these 3 categories above. And as you could see, our highest mean proportion of matching is actually for repeated. So if an examiner repeats the examination, they match on average 62% of the RACs. Reproduced is about 47%, over time 35%, and then random about 21% of the time. So this gives us a few different things. We do see our expected pattern of repeated to random. We would expect repeated, the same person on the same examination, to be able to find the same RACs more often than not. And we expect random to kind of be the lowest mean proportion because these examinations shouldn't have anything to do with each other. So now that we've discussed RACs, that was, matching, that was our first attempt. And we were able to kind of get a general sense of overall variability between whether examination was repeated or reproduced. So kind of a general sense of variability of examiners. But now we're going to focus more on individual examiner characteristics using the staple algorithm. So the staple algorithm stands for the simultaneous truth and performance level examination. So this was an algorithm designed for brain imaging in particular, and it uses an expectation maximization algorithm to estimate both ground truth and examiner performance parameters in image analysis. So this relies on the fact that we have multiple examiners examining the same image. So in the brain imaging on the right, you can see we have multiple people examine this tumor. And then, so basically you could see the green, yellow, and red are different people determining what pixels make up the tumor in this image. And then putting those 3 segmentations together, we're able to get a single segmentation estimate. And when we talk about ground truth here, in this case, it's whether or not the cell has the tumor or not. So we're able to get the full shape of the image. And then for examiner performance, we're able to see whether or not which examiners are good or not good, but which examiners perform well in the estimation of the ground truth as well. So if you look at the red and the yellow, you could see that you could kind of see this edge towards the left-hand side of the tumor. You see that the yellow and the red don't really go beyond that edge, but the green does. So you could see where multiple examinations are being taken into account, because in the final estimate of the segmentation, that is not happening. So only one examiner found those parts, so it's not part of the final segmentation. Now, how do we apply this to our example? So the one way we do this is that we basically take a examination of lab print, and this is all done post examination. So the examiners, as I mentioned, record the location of the RAC. So we have the XY location of the RAC. So what we did is we placed a grid over this RAC, over each examination, and basically whether or not a RAC appeared in that cell as determined by the location that the examiners determined. So as you can see on the right, we have the first lab print, we put the grid over it, and then in the second lab print, we have the black cells. That indicates that an examiner found a cell in that box. Now, again, the examiners do not have the grid. This is placed over afterward. So they are just examining it as if it's a regular examination. They're not looking for, oh, this cell has a RAC and this one does not. So how this relates to the previous example with the brain tumor is we now have an image with presence or absence, a binary response of whether or not a RAC is in this cell. And our entire image is going to be what we're segmenting on. And we can now kind of overlap these different grids for each examiner. And kind of to push that point across, here is one shoe example. This is the black boxes indicate which cells had a RAC determined by the location the examiner determined. As you could see, they're different across the board. So each examiner has a different idea of which cells. The shoes are aligned, so the cells should line up with each other. So as you could see towards the top, it seems to be a more top right of the shoe. It seems to be a more common area for RACs. Towards the middle, you could see that most of the examiners identified some RACs within that middle section. And then towards the bottom, you could see that A and B actually identified a few RACs here and there. C didn't really identify any in that bottom section. And then D identified quite a few across that bottom section. So I'm just kind of splitting this image in 3 different sections just to give you an idea of how different they could be. So the question is, which cells actually have RACs and which examiners correctly identify. But of course, there's no ground truth here, so we have to estimate that as well. If we knew which cells contain RACs, we could determine whether or not the examiners were able to identify that. So just to give you an idea of how prevalent RACs are across shoes, you could see that there's a couple things in this table that are interesting. If you look at a single shoe, which is each row, you could see that examiners identify different numbers of RACs. So for example, the top row, only 3 examiners examined that shoe. B and C both found about 6% of cells contain RACs, while D only found about 3%. And then if you look down each examiner column, you could see that some shoes have more RACs than others. So we could get somewhat of a sense of how much variability in RAC identification there is just by seeing, well, some people identify a lot on a particular shoe, or some particular shoes have a lot of RACs compared to others. And the cells we created tried to make sure that there was only 1 RAC per cell. So we could kind of use this as actual cell RAC prevalence. So now just to go a little deeper into the model itself. So just some notation. We have our data. Our data consists of the number of cells. So that will be N. And for us, we're going to use 1200. Then we have number of examiners. We have the binary presence or absence of a RAC in each cell. And this is again determined by the location that the examiner marked. And then we also have our true binary presence or absence. And this is actually going to be our hidden data when we talk about an EM algorithm. And then the parameters of interest are going to be the frequency of RACs. So the prevalence on each shoe. And then we define our performance parameters as the specificity and sensitivity of an examiner, with the sensitivity being the probability that an examiner found a RAC in a cell, given that cell has a RAC. And again, we don't know this for certain, so that is also estimated. And then the specificity is the probability that an examiner did not find a RAC given there was no RAC. So these are pretty general, pretty traditional definitions of sensitivity and specificity. So then our model becomes, we have our complete data, which are the observed RAC locations, which are turned into cells. And then we have our truth is going to be Bernoulli with the prevalence, because this is binary data. Our sensitivity and specificity are, as I mentioned, the probability that the observed data equals 1 in a particular cell by a particular examiner, given the truth is equal to 1. And then it's easy to show that the observed data given the truth, and the performance is Bernoulli distributed, and we're going to use an EM algorithm to estimate these unknown parameters. So going back to our example from before, we have these 4 images of cells that contain a RAC or not, determined by the examiner, and we could get a kind of a map of probabilities of whether or not a cell contains a RAC. So if there's a cell that all 4 examiners said there's a RAC in this cell, that will likely increase the probability of RAC presence. So you could see that that's kind of how this map looks on the right. And then just a table of results, you could see for this particular shoe, our prevalence is about 6%, which is similar to what we had seen going back to the previous table. We could see that the performance, the sensitivities are about 0.5. Examiner C happens to be slightly lower than everyone else. And then we have very high specificities. That's mainly due to the prevalence of RACs is very low. So there just happens to be a lot of 0 cells or cells without RACs. So examiners are good at finding cells without RACs. So some limitations of this method are that we have to examine each shoe separately. So as I showed you in this previous slide, this is 1 shoe at a time. We could get all of the parameter estimates. But what if an examiner does really well on 1 shoe, but really poorly on another? How can we kind of put that information together to give us one overall performance evaluation? So that's something that we try to tackle in extensions and our new model. Then we also make a strong assumption about cells. They're independent from each other. So we'll touch on this in a little bit more. And then again, I'm only using location. So we do have type and size of RAC. We also have the orientation that's not included yet. So to first tackle the sharing information across examinations by this same examiner, we kind of introduced this multiple shoe extension. Here we're going to assume the shoes are independent from each other, and this really allows us to average over the shoes. So we basically could get the shoe level performance for each of them, or we don't get those values, but we're basically averaging over shoes. And in our particular case, not every examiner examined every shoe. We saw that examiner A only examined a few of the shoes. So this method allows us to handle that. So here are some results. I'll point your attention to pi 5. So you can see that the posterior, the estimated mean, so these are MLE estimates, is around 0.75. We saw previously, going back, that it was 0.06. So we could see slight changes in the prevalence. But the main thing here is we could see the sensitivities are actually, for overall, are somewhat lower than that particular shoe. So that would indicate that on some shoes, these examiners do worse than they had on that one example. We could still see specificities are quite high. So now we are sharing information across shoes. There are still limitations here. We're only giving examiners a single specificity and sensitivity. So although the idea is to average over shoes, we are not, we don't have that information on each individual shoe. So there could definitely be a variation between each shoe. And then we are also assuming the examiners are independent, but given these were all for the same exam, these 4 examiners all had the same training, it's possible that they are very similar to each other, while if we had other examiners, they may be very different. These are also students, so if we included some professional examiners, it's possible that they would be very different from each other. So, but right now we're assuming that they're all independent from each other. So now how do we address some of these limitations in our hierarchical model? So what we basically do here is we introduce shoe level performance. So we're going to have PJK and QJK, which are the sensitivities of examiner J on shoe K and the specificity of examiner J on shoe K. Then we are going to have the average sensitivity and specificity for each examiner. So this is what's analogous in our staple algorithm to examiner level performance. Then we also have this examiner consistency parameter. And then another added bonus of the hierarchical model is to have kind of this population level. So we could see overall how the population average looks like. And again, in this model right now, the ground truth aspect is basically the same as the staple algorithm, but the hierarchical model allows us to kind of have a little bit more freedom to work with that. And I will discuss that a little bit more in the next few slides. So then kind of going to the graphical representation, we have this population level parameters. Then drawn from those distributions, we have our examiner level performance. And then from those distributions, we would have each examiner has their own shoe level performance. So this would allow for certain shoes to be more difficult than others. While the structure is more on the examiners, there are ways to kind of incorporate the structure on the shoes as well to incorporate more difficulty. Yeah. And then throughout this hierarchical framework, we are using mostly beta distributions. And you'll notice that instead of alphas and betas, we're actually going to parameterize by the means and parameter proportional to the variance. So that's why we use mu JPs and UPs. And our nu is the kind of the variance proponent. So the idea in the Bayesian computation, as opposed to the MLE that we did with staple, is that we have this probability model of the probability of the observed data given the truth and the performance parameters. So our goal here is to do posterior inference on all parameters rather than maximum likelihood estimation and inference using those means. So we use a modified Gibbs sampler to sample from the posterior distributions. And just a little more information on Gibbs sampler. It's basically a sampling technique that sequentially samples from conditional distributions. So we would get the distribution of T given all other parameters in the data. We would sample from T. Then using those samples, we could sample from P given all other parameters. And we do this for all of the parameters in the data. And that allows us to sample from the posterior distribution. So currently we are working on a extensive simulation study to understand how our model handles certain differences in data. So some of the key points here are we're going to look at the number of examiners. So right now we only have 4 examiners, but what happens when we increase that number? Or I mean, very unlikely that we decrease that number, but how does that vary our results? Also, the number of images. Right now, we have 15 total images or shoes that were examined multiple times. So if we increase that to 100 or so, how would that affect our results? We are also going to look at the effect of missing data on our model. So I've already discussed how some of the examiners didn't examine every shoe. So if we only have a couple of examinations per examiner, what do our results look like compared to if we had every examiner examine every shoe in the ideal setting? So we're currently working on this simulation study. Now, we do have some results from our real data set. So again, this is the same 15 shoes that we discussed in the staple algorithm. We could see that I'm just focusing on the mu-p's and the mu-q's. So these are the, this is the population sensitivity and specificity and the examiner level specificity and sensitivity. So you could see it's very obvious in the mu-p case. We have the hierarchical point estimates with their credible intervals. You could see the credible intervals overall are a little bit wider than the staple algorithm's confidence intervals, but what we do see is shrinkage towards the population mean. So if you consider the blue are MLE estimates, once we introduce this population level parameter, mu-p, we see that all the blue dots are almost moving towards that mean, which give us that red dot. So the idea of shrinkage here is very evident. And that's because of our hierarchical model, assuming that these examiners all come from the same population. But you do see that although there is this shrinkage component, the results overall are fairly similar to staple algorithm. So we are getting what we kind of expect. For the specificities, we do have some issues with the boundary. These are all very close to 1. So that is affecting our results in some case. But the values are all much higher and less variable, but there is a little bit of shrinkage, but not as much. So there are still limitations to this model. So the first being that we're still not talking about the spatial structure of the shoe. So this is kind of the assumption that each cell is independent, but that might not be the case. If there's a rack in one cell, do surrounding cells have higher chance of having racks? As you saw, there were certain areas on the shoe where that might be the case. We're also assuming the same difficulty of each examination of the shoe. So we still haven't really touched on whether or not the shoes are all different difficulty. There might be some shoes. We have touched on shoes having different examiner performance, but we haven't really touched on whether or not one shoe is more difficult than the other. This requires some sensitivity analysis with the prior distributions. And one limitation that's actually in all of the methods is the location is subject to measurement error. So we kind of address this with the number of cells we choose. So we chose cells that the 1200 cells is based on that measurement error. So then I have ongoing and future work that we're working on now. And mainly there to address some of the limitations that I've already discussed. So the first one is we're going to continue to work on our fully Bayesian analysis. This includes conducting the simulation study, which is a big part of building our model to understand how it will change based on the data. The next is to kind of build an autoregressive model for rack location. So this will ease the independent assumption. And then another step that we might into is clustering examiners based on performance. Right now, we only have 4 examiners, so this task is difficult with our current data set. But the idea is that instead of a single population mean, can we identify multiple populations? And then just some overall summaries. The first two are mainly based on the model, and then just to kind of drive some of the key insights that we found so far, from an application standpoint. So the first one is that our model does perform similarly to the staple algorithm. So we are getting means similar to the means estimated in staple, but obviously we also have the added bonus of the population mean, which has that shrinkage component. We also have the shoe level performance. So we do have some added bonuses over the staple algorithm. Another key summary here about our model is that we're focusing on RAC identification rather than the final decision. So in all of these, in all this research, we're really trying to see how RAC identification is different across examiners, which hasn't really been done very much. And then just some of the key things that we found in our analyses. So as I mentioned before, in repeated examination, 62.4% of RACs matched in the repeated pairs, and this got worse as we kind of expected, with random pairings having about 21% matching of the RACs. We do see that student examiners perform somewhat low, 35 to 43% sensitivity, but there is very little variation between the examiners. Now, that was more evident in, so we have variability parameters that we didn't really discuss here, but we also saw that the means were very similar to each other, even with the shrinkage towards the population mean. Again, I say the performance is somewhat low, but we really don't have a reference group to compare that to. That might not be considered low. And then if we do consider this kind of lower performance, we do know that the RACs are very rare. So estimated like 0% to 10% of the cells contain RACs, depending on the shoe. So that indicates that finding a RAC is very difficult. So that would kind of play into lower performance of finding RACs, given they're actually there. And that wraps up my talk. So thank you. And are there any questions? I saw some pop up. So.
I do want to thank you, Corey, again for presenting this material and for joining us today. And thank you all for joining us. I'll share these quick slides with you while we allow people to put questions in the Q&A. Just quick reminder that our upcoming events, May 25th, we have another webinar focusing on algorithms in forensic science. And then on June 14th, we have our CSAFE-wide field update with some insights from the inside, things that are coming up next, and again, looking at applying algorithms in forensic science analysis. And then I also would like to encourage you all to fill out the evaluations that have hit your email inboxes. I promise you this is a quick evaluation. I know that this is usually the least favorite part of everyone's experience, but the average time it takes to fill out my evaluation is 2 minutes. So if you could join us, give us your feedback, we'd really appreciate that. I'm going to turn it back to here, and Corey, if there are questions, it looks like the only one I'm seeing right now is somebody wondering if there's a copy of the presentation. Corey, I'm going to leave that up to you, and I won't put you on the spot, but if Corey approves, we will share the slides when we also share the recording that will be made available in public on our YouTube.
Yeah, we could discuss, we'll discuss that afterward. I'm sure it will be though, so, because the YouTube video is there anyways.
Sure.
Yeah. And then another question, is there any parameters for stack peel issue? So Yeah, so we haven't really touched that much on the shoe sole itself. Right now, we only have the data from a single type of shoe. So because we only have one shoe, we don't have that in our case, but it's definitely something we could consider. But this kind of comes back to contact surface, which there's been some work on. So if there is a heel, then that could reduce your contact surface. So that is planned to be incorporated into our model in the future. And this kind of also goes back to like that spatial structure of the data. Let me talk more about how students were trained and how they marked RACs. So I know that the students were trained by professional examiners with the Israeli police force. So I know the extent of their training was fairly short compared to probably professionals. I think it was about, if I remember correctly, an 8-hour session. I might be wrong on that though. And they did the examination the way that the shoe print examiners in that lab did the examination. So I believe they used the computer-aided system that lab designed. So I know they use that because all the variables come from that computer software. It's one of my references. Let me take the paper that this data comes from, or the system that is used is Wisner et al. 2020 data set of digitized RACs and their rarity. So that has all the information about how this data was collected because it was collected in a similar manner. Yeah. And then just a comment. So I do use the term examiners in this. I also use the term markers. So examiners is for the more general model. I tried to keep that terminology. I apologize if I kind of twisted that up a bit. So I was trying to refer to the students as markers. But yeah, they're not professional examiners. Right now, we don't have likelihood ratios of the results in our model, but that's definitely something we are going to look at. And that would be more related to kind of, like the evidential, I assume, likelihood ratios that you're discussing. Right now, we don't have that in our model.
Corey, thank you again. Thank you all for joining us, and we hope you have a great day.